When we store data in a standard array, the computer sets aside a single, unbroken block of memory. If you allocate a 4-slot array, those 4 slots must sit directly next to each other. This structure makes finding an item fast, but it creates a massive restriction when you try to expand. Suppose you want to add a 5th element, but the very next memory slot is already occupied by another program. The array cannot simply jump over the roadblock. It is stuck. Even if your system has plenty of total free space scattered across other locations, the array cannot use it because it demands strict, continuous order. This fragmentation means memory is wasted, and resizing your data becomes an expensive operation of copying everything to an entirely new location. We need a data structure that can break free from this restriction and utilize scattered space efficiently. To bypass the limitation of rigid, side-by-side memory blocks, we have to look at data differently. Instead of forcing elements to live together in a single row, we can scatter them anywhere in memory where room exists. We achieve this using a structure called a node. A node is a simple container divided into 2 distinct parts. The first part holds the actual data you want to save, like an integer, a string, or an object. The second part holds a critical piece of metadata, a pointer, which is the exact memory address of the next item. Think of a node like a clue in a treasure hunt. The clue gives you an item or information, but it also explicitly tells you exactly where to walk to find the next step. By giving every individual piece of data its own map to the next item, we no longer need our data to sit in a consecutive block. When we connect these nodes together by having each one point to the next, we form a singly linked list. This chain relies on specific markers to function safely and predictably. The very beginning of our list is tracked by a special reference known as the head. The head does not store data itself, it simply points to the first actual node in our sequence. From there, we follow the trail from one node to the next. Because each node only knows about the item ahead of it, we can only move forward in one strict direction. This creates a critical vulnerability. If you accidentally lose or overwrite the head pointer, your program loses the entry point. The rest of the chain becomes entirely unreachable in memory, floating adrift. The chain finally ends when the last node's pointer contains no address at all, a state we call null, signaling that the sequence is complete. Finding a specific element inside a linked list requires a patient, step-by-step approach. In a standard array, if you want the 4th item, you can jump directly to index 3 using basic math. A linked list cannot do this because the computer does not know where the nodes are hidden until it reads the pointers leading to them. To find a target value, we must start at the head and physically inspect the first node. If it is not what we want, we read its pointer to move to the second node, then the third, and so on. This sequential walk is called traversal. Because the time it takes scales directly with the number of elements, searching has a linear time complexity, or big O of n. While this makes lookups slower than an array, this exact structural layout unlocks massive advantages when it comes to changing the data. Modifying data is where the linked list displays its true strength. Imagine trying to insert an element into the middle of an array. To make space, every single subsequent item must be shifted down by one slot in memory, which is a highly tedious process if you are dealing with thousands of entries. In a linked list, inserting a new element requires 0 data shifting. If we want to place a new node between 2 existing ones, the operation is remarkably clean. We look at the node that should come before our new data. We take its pointer, which currently links to the next neighbor, and rewrite it to point directly to our new candidate node instead. Then, we take the pointer of our new node and attach it to the subsequent neighbor. By breaking a single bond and establishing 2 new connections, the new element is instantly woven into the fabric of the list. Deleting data from a linked list operates on the exact same elegant principle of rerouting pointers. When you want to remove a node from the middle of the chain, you do not need to clear out memory slots or shift the rest of the collection backward to close the gap. Instead, you simply bypass the target node entirely. You take the pointer of the node immediately preceding the one you want to delete, and stretch it forward to point directly to the node that follows the target. Once this adjustment is made, no active pointers in your program reference the old node. It is effectively cut out of the sequence. The computer system handles the rest, identifying the isolated node as unused and safely reclaiming that memory through garbage collection, leaving your remaining chain flawlessly intact. Choosing between an array and a linked list always comes down to balancing these performance trade-offs. Arrays are the undisputed masters of fast random access, allowing you to instantly read any index at any time, but they suffer from rigid memory requirements and slow insertions. Linked lists give up that instant lookup capability, forcing you to traverse items linearly, but they grant incredible flexibility. They allow your data to expand dynamically across fragmented memory spaces, and they make insertions and deletions highly efficient, fixed-time operations. Understanding these core mechanical differences ensures you can pick the exact right tool for your program's specific performance needs.